Welcome! In this session, we'll be solving LeetCode problem number 1299, replace elements with greatest element on right side. This problem challenges us to manipulate an array efficiently by replacing every element with the greatest element to its right. We'll explore different approaches and analyze their trade-offs. Let's dive in. The problem asks us to modify an integer array such that each element is replaced by the greatest element among the elements to its right. For the last element in the array, we simply replace it with -1. Once this transformation is complete, we return the modified array. For example, given an input array ARR equals 17, 18, 5, 4, 6, 1, the output should be 18, 6, 6, 6, 1, -1. Each element has been replaced based on the greatest value found to its right. The input array can have a length between 1 and 10,000. And each element is a positive integer between 1 and 100,000. Finally, the output will also be an integer array where all elements are updated according to the given rules. Let's consider the explanation for the first example. At index 0, the value 17 is replaced by the greatest value in the subarray, 18, 5, 4, 6, 1. The maximum here is 18. At index 1, the value 18 is replaced by the greatest of 5, 4, 6, 1, which is 6. For index 2, the value 5 is replaced by the greatest of 4, 6, 1, again yielding 6. At index 3, the value 4 is replaced by the greatest of 6, 1, which is 6. At index 4, the value 6 is replaced by the greatest value of 1, giving 1. Finally, the last element 1 at index 5 is replaced with -1. For the second example, where the input is a single element array ARR equals 400, there are no elements to the right, so the single value is replaced with -1, resulting in the output, -1. Now, take a look at another example with the input ARR equals 7, 1, 3, 2. At index 0, the value 7 is replaced by the greatest value in the subarray 1, 3, 2, which is 3. At index 1, the value 1 is replaced by the greatest of 3, 2, yielding 3. At index 2, the value 3 is replaced by the greatest in 2, which is 2. Lastly, at index 3, the value 2 is replaced with -1 because it is the last element in the array. The output for this example is 3, 3, 2, -1. The constraints ensure that the array has at least one element and at most 10,000 elements, with each element being a positive integer between 1 and 100,000. This means the algorithm must handle both small and large input sizes efficiently. Some edge cases to keep in mind include when the array contains only a single element. For example, if ARR equals 42, the output will simply be -1, since there are no elements to the right. If all elements in the array are equal, such as ARR equals 5, 5, 5, 5, the output will be 5, 5, 5, -1. Because the replacement at each step will still be the same value until the last element. For arrays sorted in strictly decreasing order, like ARR equals 10, 9, 8, 7, the output will be 9, 8, 7, -1. Finally, we need to ensure that the solution efficiently handles cases with the maximum constraints, such as an array with values like 100,000, 99999, 1. This emphasizes the importance of designing an optimized approach to solve the problem within the given constraints. To solve the problem of replacing each element in the array with the greatest element on its right, we explored two main approaches, brute force and an optimized reverse traversal. Let's begin with the brute force approach. The intuition here is straightforward: replace each element by finding the maximum value among all the elements to its right. This involves two nested loops. The outer loop iterates through each element of the array, and the inner loop finds the maximum in the subarray starting from the next element to the end. Finally, the last element is replaced with -1, as there are no elements to its right. However, this approach has significant downsides. The time complexity is n squared, since, for each element, we traverse all subsequent elements, leading to redundant computations, especially for overlapping subarrays. Despite being simple to implement, this inefficiency makes it unsuitable for larger input arrays. Now, we turn our attention to the optimized reverse traversal approach, which is both more efficient and elegant. The key insight here is to avoid recalculating the maximum repeatedly by using a variable, max_right, to dynamically store the greatest element seen so far from the right. We start by initializing max_right to -1 because the last element will always be replaced with -1. Then, we traverse the array from right to left. For each element, we temporarily store its current value, replace it with max_right, and then update max_right to the maximum of its current value and the previous max_right. This ensures that max_right is always the largest element encountered so far during the traversal. The beauty of this approach lies in its efficiency. It processes each element in a single pass, giving us a linear time complexity of O(n). Additionally, because we only use one extra variable, the space complexity remains constant at O(1). This dynamic tracking of the maximum value eliminates redundant calculations and allows us to modify the array in place. When comparing the two approaches, the brute force method is simpler to implement but computationally expensive, making it impractical for larger arrays. It's better suited for small input sizes where performance isn't a concern. On the other hand, the optimized reverse traversal approach, while slightly more complex conceptually, is much more efficient. Its linear runtime and constant space usage make it the clear choice for handling large datasets. By dynamically updating the greatest element using max_right during the reverse traversal, we avoid redundant work and achieve a highly performant solution. For these reasons, the optimized approach was chosen as the preferred strategy. It strikes the ideal balance between efficiency and scalability, solving the problem elegantly and effectively. The task in this problem is to transform an array so that each element is replaced by the greatest value among the elements to its right, with the last element being replaced by -1. For example, if the input array is 17, 18, 5, 4, 6, 1, the output should be 18, 6, 6, 6, 1, -1. Now, solving this efficiently is the main challenge. A straightforward approach, where we check every element to the right for each position, would take O(n²) time, which becomes unmanageable for large arrays. Additionally, we want to achieve this transformation using O(1) extra space, modifying the array directly. The optimized solution leverages a reverse traversal of the array. By iterating from the last element to the first, we can maintain the greatest value seen so far and update each element in constant time. This approach drastically improves the time complexity to O(n). To implement the optimized solution, we start by initializing a variable max_right to -1, as this represents the greatest value to the right of the last element, which is always replaced by -1. We then traverse the array from right to left, beginning with the last element and moving toward the first. For each element, we store its current value in a temporary variable called current. This ensures we don't lose the original value before updating it. Next, the element at the current index is replaced with the value of max_right, which represents the maximum value encountered to its right so far. Finally, we update max_right to be the maximum of its current value and the value stored in current. Once this loop completes, the array will have been transformed in place, with each element replaced by the greatest value to its right. Let's walk through the example array 17, 18, 5, 4, 6, 1 step by step. Initially, we set max_right to -1. Starting with the last element, we store its value, which is 1, in the variable current. The last element is then replaced with max_right, resulting in the array 17, 18, 5, 4, 6, -1. We then update max_right to the maximum of -1 and 1, which is 1. Next, we move to the second to last element, where current is 6. We replace this element with max_right, giving us 17, 18, 5, 4, 1, -1. Max_right is updated again, this time to the maximum of 1 and 6, which is 6. Following this pattern, we continue traversing leftward. The third to last element, 4, is replaced with max_right, 6, and max_right remains 6. Similarly, the element 5 is replaced with 6, and max_right stays at 6. When we reach the second element, 18 is replaced with 6, and max_right becomes 18. This step-by-step traversal ensures that each element is transformed correctly. Finally, for the first element, we store its value, 17, in current. We replace it with max_right, which is 18, resulting in the fully transformed array 18, 6, 6, 6, 1, minus 1. At this point, max_right is updated to the maximum of 18 and 17, which remains 18. This completes the reverse traversal, and the output array is ready. A few key insights emerge from this process. First, reverse traversal allows us to propagate the maximum value in a single pass, avoiding redundant comparisons. Second, the transformation is done in place, modifying the input array directly and ensuring 1 additional space usage. The algorithm is also highly efficient, as each element is visited only once. Additionally, it handles edge cases seamlessly, such as replacing a single element array with -1, returning an empty array as is, and correctly processing arrays with all identical elements. The algorithm utilizes minimal data structures, relying only on the input array and a single variable, max_right, to track the maximum value during the traversal. This ensures in-place transformation without requiring additional storage. In terms of complexity, the solution is highly efficient. The time complexity is O(n), where n is the array's length, since we make just one pass through the array. The space complexity is O(1), as no extra data structures are used beyond the input array and the max_right variable. This optimized use of resources makes the solution ideal for large arrays, addressing both performance and space constraints effectively. The given Python code solves LeetCode problem number 1299, replace elements with greatest element on right side. The problem requires transforming an input array such that each element at index I is replaced with the greatest element among the elements to its right, with the final element replaced by -1. Explanation. 1. Initialization. The solution starts by initializing the variable greatest to -1. This value represents the greatest element to the right of the current index as we traverse the array. The last element will always be replaced by -1, so initializing greatest to -1 simplifies the logic. 2. Right to left traversal. The array is traversed in reverse order, from the rightmost element to the leftmost one. This ensures that at each iteration, we have already processed all elements to the right of the current index. 3. Key steps in the loop. The current value of the element at index I is temporarily stored. This is necessary because I will be updated in the next step. The current element is replaced with the value of greatest, which holds the maximum element encountered so far to the right. The greatest variable is then updated to the maximum of its current value and the current value, the original value at index I. This update ensures that greatest always holds the maximum value of all elements processed so far. 4. Return value. After the loop completes, the transformed array is returned. Complexity analysis. Time complexity. The solution processes each element of the array exactly once, making it O(n), where n is the length of the array. Space complexity. The solution uses only a constant amount of extra space, O(1), as the transformation is done in place. Example walkthrough. Consider the input array ARR equals 17, 18, 5, 4, 6, 1. Start with greatest equals -1. Traverse from right to left. Index 5, replace 1 with -1, update greatest to 1. Index 4, replace 6 with 1, update greatest to 6. Index 3, replace 4 with 6, greatest remains 6. Index 2, replace 5 with 6, greatest remains 6. Index 1, replace 18 with 6, update greatest to 18. Index 0, replace 17 with 18, greatest remains 18. Final output, 18, 6, 6, 6, 1, -1. This efficient and concise approach ensures correctness while minimizing both time and space usage. This is the Java implementation for LeetCode problem number 1299, replace elements with greatest element on right side. The solution mirrors the logic of the provided Python implementation. It uses a right-to-left traversal to replace each element with the maximum element to its right, updating the maximum value dynamically. Key differences include Java's need for explicit type declarations and the use of the math.max method for comparisons. We begin with the first example where the input array is 17, 18, 5, 4, 6, 1. Initially, the variable greatest is set to -1, as there are no elements to the right of the last index. Starting from the rightmost element, which is 1 at index 5, we replace it with the current value of greatest, resulting in the array becoming 17, 18, 5, 4, 6, minus 1. Then, we update greatest to be the maximum of its current value, minus 1, and the original value at index 5, which is 1. So, greatest becomes 1. Next, we move to index 4, where the value is 6. Here, we replace it with the current greatest, updating the array to 17, 18, 5, 4, 1, minus 1. The greatest is then updated again to the maximum of 1 and 6, resulting in greatest becoming 6. At index 3, the value is 4. We replace it with the current greatest, modifying the array to 17, 18, 5, 6, 1, minus 1. Since the maximum of 6 and 4 is still 6, the value of greatest remains unchanged. Continuing to index 2, the value here is 5. We replace it with the current greatest, updating the array to 17, 18, 6, 6, 1, minus 1. Again, the maximum of 6 and 5 is 6, so greatest remains 6. Next, we move to index 1, where the value is 18. Replacing it with the current greatest changes the array to 17, 6, 6, 6, 1, minus 1. This time, greatest is updated to the maximum of 6 and 18, making greatest now 18. Finally, at index 0, the value is 17. Replacing it with the current greatest updates the array to 18, 6, 6, 6, 1, minus 1. Since the maximum of 18 and 17 is still 18, greatest remains unchanged. With this, we have processed all elements, and the final output for this example is 18, 6, 6, 6, 1, minus 1. In the second example, the input array contains only one element, which is 400. Here, we set greatest to minus 1 initially. Starting with the only element at index 0, the value is 400. We replace it with the current greatest, resulting in the array becoming -1. Then, we update greatest to the maximum of -1 and 400, which gives 400. As there are no more elements to process, the final output for this example is simply -1. Now, let's consider the third example with the input array 1, 2, 3, 4, 5. We start with greatest set to -1. At index 4, the rightmost element is 5. Replacing it with the current greatest updates the array to 1, 2, 3, 4, -1. Then, greatest is updated to the maximum of -1 and 5, making greatest equal to 5. Moving to index 3, the value is 4. Replacing it with greatest modifies the array to 1, 2, 3, 5, -1. The maximum of 5 and 4 is still 5, so greatest remains unchanged. At index 2, the value is 3. Replacing it with greatest updates the array to 1, 2, 5, 5, -1. Again, the maximum of 5 and 3 is 5, so greatest stays the same. At index 1, the value is 2. For the element at index 1, we replace it with the current greatest, resulting in the array becoming 1, 5, 5, 5, -1. The maximum of 5 and 2 is still 5, so greatest remains unchanged. Finally, at index 0, the value is 1. Replacing it with greatest updates the array to 5, 5, 5, 5, -1. Again, the maximum of 5 and 1 is 5, so greatest remains 5. Having processed all elements, the final output for this example is 5, 5, 5, 5, -1. The time complexity of the solution is O(n), where n is the length of the input array. This is because the algorithm processes the array in a single traversal, moving from right to left. During this traversal, the algorithm performs 3 constant time operations in each iteration. First, it stores the current element in a temporary variable, which takes O(1) time. Then, it replaces the current element with the greatest value observed so far, another O(1) operation. Finally, it updates the greatest value by comparing it to the current element, which also takes O(1). Since these 3 operations are performed for each of the n elements, the overall time complexity becomes O(n) multiplied by the constant cost of these operations, which simplifies to O(n). Importantly, this efficiency holds true for all cases, whether the input array is sorted, reversed, or unordered, because the algorithm always traverses the array exactly once. The space complexity of the solution is O(1), meaning it uses a constant amount of additional memory regardless of the input size. This is achieved by modifying the input array directly, so no extra space is required for storing the result. The only additional memory used is for two integer variables, one called greatest, which keeps track of the maximum value encountered so far, and another temporary variable called current, which holds the current element during each iteration. Both of these variables require O(1) space individually, and no other data structures or recursive calls are involved in the algorithm. As a result, the total additional space usage remains constant, leading to an overall space complexity of O(1). Comparing this optimized approach to a brute force solution highlights its efficiency. In a naive method, you would use a nested loop to find the greatest element to the right of each element. The outer loop iterates over the n elements, and for each element, the inner loop scans the remaining elements to its right. This results in a total of n iterations for the outer loop, and approximately n iterations for the inner loop in the worst case, leading to a time complexity of O(n) multiplied by O(n), or O(n squared). In contrast, the optimized approach avoids the nested loop entirely by using a single traversal from right to left, reducing the time complexity to O(n). Regarding space usage, both the brute force and optimized solutions modify the input array in place, so their space complexity is the same, O(1). Finally, the linear time complexity of the optimized approach can be mathematically verified since the number of operations directly scales with the size of the input. Doubling the size of the array doubles the number of iterations, confirming that the time complexity is O(n). With no additional space required beyond a few variables, the space complexity remains constant at O(1). When solving this problem, there are a few common mistakes to watch out for. First, if you're using the optimized approach, always remember to iterate from right to left. Iterating forward, or from left to right, will result in incorrect answers because the greatest element to the right of the current position hasn't been processed yet. Next, in the brute force method, it's easy to get tripped up by off-by-one errors in the inner loop. Always double-check your loop boundaries to ensure that you are comparing only the elements strictly to the right of the current position. Another common oversight is forgetting to initialize the greatest so far variable correctly in the optimized approach. This variable should start at -1, which is the value for the last element in the result array. If you skip this step, your solution might produce unexpected results. Finally, don't overlook edge cases, such as arrays with only one element. For single-element arrays, the output should simply be -1. Missing these edge cases can lead to runtime errors or incorrect outputs, so ensure your solution is robust enough to handle them explicitly. Now, let's talk about some common misunderstandings and key insights for interviews. One mistake candidates often make is overestimating the time complexity of the optimized approach, thinking it's O(n squared instead of O(n). It's important to understand that the reverse traversal processes each element exactly once, resulting in linear time complexity. From an interview perspective, this problem is a great example of how reverse traversal can be used to optimize both space and time efficiency. It also tests your ability to recognize patterns like maximum so far and apply them effectively. Be prepared to discuss the trade-offs between the brute force and optimized approaches. For instance, the brute force method is intuitive but impractical for large input sizes due to its O(n squared) time complexity, whereas the optimized approach avoids redundant comparisons. Also, interviewers often look for your ability to handle edge cases, such as empty arrays, single-element arrays, or arrays where all elements are identical. Bringing these up proactively can demonstrate a thorough understanding. Lastly, anticipate follow-up variations like replacing elements with the smallest value on the right instead of the greatest, or modifying the array in place without using additional space. These variations test how adaptable your solution is to changes in requirements. This problem also connects to several related problems that can help you strengthen your understanding of similar techniques. For instance, LeetCode 238, product of array except self, involves using auxiliary variables and specific traversal patterns to optimize both space and time complexity. Then there's LeetCode 42, trapping rainwater, which requires calculating left and right bounds for each element, a concept that parallels maintaining the greatest element in this problem. LeetCode 121, Best Time to Buy and Sell Stock, is another good example, as it focuses on tracking maximum or minimum values during array traversal, using the same greatest so far idea. Lastly, LeetCode 978, Longest Turbulent Subarray, tests your ability to recognize and handle subarray patterns. It often requires careful traversal and edge case handling, which are also critical for solving this problem. When discussing alternative approaches, the brute force method is a starting point. It works by iterating through all elements to the right of each element to find the maximum. While its simplicity makes it easy to implement, the O(n²) time complexity makes it impractical for large arrays. This highlights the importance of understanding both the trade-offs and the limitations of different approaches. The optimized reverse traversal approach is the most efficient solution to this problem. It works by iterating through the array from right to left while maintaining a greatest so far variable. This ensures that you always have the correct value to replace the current element. The time complexity is O(n), as each element is processed exactly once, and the space complexity remains O(1). However, implementing this approach requires a solid understanding of reverse traversal patterns and careful initialization of the greatest so far variable to avoid errors. For a more theoretical discussion, you might consider a divide and conquer approach. This involves splitting the array into two halves, solving for each half, and combining the results. While this method typically has a complexity of O(n log n), depending on the merging process, it's less practical than the optimized approach. Nevertheless, it's a useful strategy to discuss in interviews as it demonstrates your ability to explore alternative solutions. Understanding these trade-offs will help you explain your thought process clearly and show that you're thinking critically about the problem. Great job! To summarize, we tackled a common array manipulation problem and explored both brute force and optimized approaches. Remember to practice reverse traversal and in-place solutions. Thank you for watching. Like and subscribe for more coding content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!